All right, so I now got a new category of post-quantum cryptography. This stuff is very new, and it's what we should all be using, and it's very hard. I couldn't find any good tutorials that made any of it comprehensible, except for this one called Baby Kyber. There are 3 algorithms I know approved by the NIST so far, and this one is the public key encryption algorithm. The others are signature algorithms, and they're very baffling, and I cannot find anybody that explains them in simple terms. But there are 2 papers that describe Baby Kyber very well. There's one, let me point them out here. If you go to the end, there's 2 papers that I based all this on, which you might want to check out. This one here explains the theory, and you can do it without any computing at all. You just do it by explains how it works, which is what we're going to go through here. And the next one did a Python implementation, which we're also going to use. So I combined what I found in these 2 papers to implement what they call Baby Kyber. So this is the public key encryption that is going to replace all the others because it is not subject to being cracked by quantum computers. And it's called Crystal's Kyber because for some reason they decided that all the post-quantum encryption schemes will be named after science fiction crystals. And I guess a Kyber is the crystal in a lightsaber in Star Wars. The signature algorithm is crystaldilithium, and they got other ones. So for some reason they're naming after science fiction, but anyway, that's what they are. So here's how Kyber works, and we're going to use Baby Kyber, which is just like the first RSA project. We used some really small numbers so you could understand the math easier, and Baby Kyber is the same way. It shows you how it works with very small numbers, so it's easier to do. So to generate the keys, now what you have to do is you have to have a vector of polynomials, which you'll see, and you just choose random small coefficients. That's the private key. Then you have Q, which is a modulus for the coefficients here, and you have a modulus for the polynomials themselves that is always x to the 4th plus 1. And one thing that is very strange about this is you have some equations in this number x, and you have this number x referred to here, and you never evaluate anything in x. You're just performing operations with systems by combining, multiplying together polynomials, but you never actually evaluate it for any value of x. It's kind of screwy that way. And then you have A as a matrix of random polynomials, E is a small error values, and this is something you calculate from it. And the public key involves this calculated number. And the reason this works is because you add random errors to it during the process of encryption. So the answer has random variation, and you have to remove that later. And the purpose of the random variation is it means you cannot use analytical methods of combining the polynomials to extract the key. That is called learning with errors. You send a noisy signal. At the other end, you round it off to get rid of the noise, which will work if you have the key, but you cannot get in there without the key because the noise confuses your attempt to derive the key. That's the hard problem here, is called learning with errors. So to generate your private key, you just make it up. You just use small numbers here, so I'm just using -1 and 1, and you have polynomials, and for Baby Kyber, we're going to use a maximum power of 3. So all we have is 4 possible terms: cubes, squares, x to the 1st, and constants, 1. And so here I just choose -1, and 1, and 0 for the 4 possible parameters. Those are the coefficients. So this is the first randomly generated vector, and this is the second one. Or no, this is a vector. It's technically a vector because it is 2 polynomials. It's a vector in 2 dimensions, and the 2 dimensions each contain a polynomial. So it's a little screwy, but it turns out the math is not too hard. So that's the secret key. And it doesn't have to have prime numbers or anything. It just has to have small values. And you make a public key generation, you choose a modulus, and we're going to use Q equals 17 modulus. So now we create a matrix of random polynomials, and the coefficients are taken modulus Q, so the coefficients have to be between 0 and 16, and again, you don't have to use prime numbers or anything, you just use any random numbers at all. So you make, here's the structure of all these polynomials: 6x cubed plus 16x squared plus 16x plus 11, and just make up other ones. So there's a matrix. Now you make some errors, and the errors are again polynomials. They just have to have small coefficients. Here you have big ones going up to like 16. Here you make them real small, like only 1 or -1. because the errors have to be small or you won't be able to remove them at the end. Now you calculate t, which is going to be the public key, by as plus e. And this is how it looks. This is a matrix of 2 by 2 polynomials. Here's a vector of 2 polynomials, and then you're going to add these errors here. So the way you do matrix multiplication is you take this. Remember, I learned this long ago. Your one hand goes this way and one hand goes this way. Your left hand goes horizontal and your right hand goes vertical. So you take this one times the top plus this one times the bottom, and that's what goes on top. And in the bottom row, you take this one times the top and this one times the bottom, and that's what goes in the bottom. That's how you do matrix multiplication. And then you add these things. So the top term is this quantity here times this quantity here. Let me highlight that better. My mouse will not let me do it. All right, here, plus this quantity, the 9 times the minus x, plus the top element here, x squared. That's what the top term is going to be. And so you just multiply it out. 6x cubed, this gives you minus 6x to the 6th, minus 6x to the 5th, by this times that. This time that is 6x to the 4th. And then you have the 16 turns in here, and 16x to the 4th, and 11. And I've just lined them up so coefficients in the same power are vertically lined up. Then you take the next one, 9x cubed times minus x cubed is minus 9x to the 6th. And you have minus 9x to the 4th, because you take a cube times x to the 1 here. You have 4x squared is going to turn into minus 4x to the 5th, minus 4x cubed. And so you go. 6, 3 is here. So these terms come from the first multiplication. And these, all through the 11. Those, my mouse is just not letting me highlight the stuff I want. All right. I'll give it one more try to get this thing to highlight just what I want and not everything. There. That stuff comes from here. And this stuff comes from here. And then you have x squared at the end. So you just add it up and you get a polynomial. Now, it's 6th order. Now, the polynomial, the whole expression, is calculated modulus f, and you set f to x to the 4th plus 1. And what that means is x to the 4th is going to be minus 1 in that modulus. So you can take these high-order terms that contain x to the 4th and higher, and you can take out an x to 4th and make it minus 1. So if you take an x to the 4th out of here, you get 15x squared. Minus 15x to the 6th is 15x squared, because the x to the 4th is just minus 1. This one, you have 26x, and you change the sign, because x to the 4th is minus 1. This minus 41x to the 4th is just plus 41, because x to the 4th is minus 1. And the rest you leave unchanged. Now you can combine these. There's an x term and an x term here that will combine. So this is the final answer. 18x cubed, 15x squared, 34x, plus 41. But there is one more step, because remember, these coefficients are on a modulus ring of modulus 17. So 18 minus 18, this is something I made a mistake on a few times, minus 18, you can add 17 and get to minus 1, but you have to add 17 again and get to 16. Because the modulus means you're going to get up to 0 to 16. So 15 is already the right modulus. 34 is 2 times 17, so it's 0 modulus 17, so this term vanishes. 41 is 2 times 17, 34, plus 7, so it's 7. So this is the final polynomial you create. That is t. This is the first term of t, the top term of the matrix. We're calculating this number. So there are 2 polynomials we're going to get in the vector, and this is the top term. All right. Then you do the bottom term the same way, and you end up with t, which is this. So now, here's the final results. There's the private key. There's the public key is A, T, where A is this mess and T is that mess. So it looks kind of screwy, but the math is actually not very advanced. It's just multiplying polynomials together. So now, there's a challenge where you create another public key, and you can do it by following this carefully. But after I did it, it's actually extremely difficult to do this and get the right answer, as you can imagine. I kept on making mistakes somewhere in here, especially, and also mistakes when I took the modulus. So it's tricky, but you can do it by hand. However, you don't have to. You can do it in Python. And so I took a Python implementation and uploaded it to my server so you can just download it and use it. And so this is the way to do exactly what we just did in Python. And I put it in Google Colab. So I download the Kyber library, and for some reason my server will not let you download a Python file. It regards it as malware or something, so I have to give it a different name and then change the name later. Then you import all these functions, and now these are the parameters. Now, one thing to understand is how these parameters relate to the equations we've talked about previously. And I'd like to get them both on the screen at the same time if I can do it. Okay, the private key is minus x cubed minus x squared plus x. And that is s. You see s here, 0, 1, minus 1, minus 1. These things are by convention, in normal mathematics, you put the higher power of x to the left. But in this Python implementation, you put the lower power to the left. So this has 0 1s, 1x, minus 1 for the others. So you read it right to left. It's 0, 1, minus 1, minus 1 is how you put this in Python. And this one is going to be 0, minus 1, 0, minus 1, because you have minus x cubed minus x. So that's what's going on here. This is the secret key, but the only thing you put in here is the coefficients going from the 1s to the high power of x, which is the opposite of the normal way you write a polynomial. That's the only confusing part. So down here, if you look at A, you read it from right, 11, 16, 16, 6. 11, 16, 16, 6. Then you read this one from the right, 3, 6, 4, 9, 3, 6, 4, 9. Then the next one is 1, 10, 3, 5. There it is, 1, 10, 3, 5. And the next one is 15, 9, 1, 6. 15, 9, 1, 6. That's how you build the A. Then you have the error term, which is just anything you want. I think we did define it somewhere up here. Yep, that's what we're going to use for errors. X squared and x squared minus x. So this is going to be no 1s, no x's, 1x squared, and no x cubed. So it's going to be 0, 0, 1, 0. That's the first block. And this one here is going to be no 1s, minus x, plus x squared, and no cubes. So it's going to be 0, minus 1, 1, 0. And that's what you see here, 0, minus 1, 1, 0. And that's the noise term. So you calculate t here, and that will print it out. So when I run this, it's going to download code from my server, and then import the library, and then calculate t. So there's t, and let's compare that value of t to the value we calculated by doing all this stuff by hand. When we were all done with that mess, we got this. The top term, this is 7, 0, 15, 16. And there it is, 7, 0, 15, 16. This one is 6, 11, 12, 10, and there it is, 6, 11, 12, 10. So you can do it with Python. You don't have to do it by hand. So now there's the results, and there's a challenge to do here. All right, and there's another challenge to do down here. Now that you have this library, now we should talk about encryption and decryption. To do encryption, you have to have a randomizer polynomial and 2 error polynomials, as random small coefficients, and then a message. And the only message we can send with Baby Kyber is 4 bits. It's not long enough to do anything good, but it is long enough you can see how it works. So here's what we're going to do. Here's a random polynomial with small values. The randomizer, here's 2 errors. These are just all random values. Random with small values, so I just use plus, minus 1, and 0. We encode the message using bits as coefficient. So I want to encode 1, 0, 1, 1. So I take 1x cubed plus 0x squared plus 1x plus 1. That is the encoded message. All right. Now, the message, if I left it like this, it would be overwhelmed by the errors. So what you do is you amplify the message to make the signal bigger than the noise. You multiply it by half the modulus, round it up. So that's 9, because the modulus is 17. Half of that is 8.5. You round it up to 9. So for the message, we use 9x cubed plus 9x plus 9. That is encoding this 1, 0, 1, 1, so it's larger than the errors. And so here's the encryption process. You do A transpose times the randomizer plus an error for you, and you do T transpose times the randomizer plus another error plus the message here. And those 2 things are the encrypted message. And you decrypt using another formula down here. And this is annoying to do by hand, so I'm just going to use the library. So here's what you get if you do this stuff in Colab, where I recommend doing everything when possible. All right. So the encrypted message turns into this. First a vector with two polynomials, and then a single polynomial, that's u and v. And when you decrypt it, you get 1101, which is the 1011 backwards again, of course. So that's how it works. And so you got an encryption challenge here you have to put in, and then you can do decryption alone. Now we did decryption there, but one thing about decryption that's worth seeing is you really don't need very many of those parameters for decryption. You won't know any of the errors. You're going to wash out the errors. All you need to know is the modulus for parameters, the modulus for x, and then the secret key, and then the encryption, u and v. And then you can just decrypt the thing. Because what happens is you decrypt it and then you round it off. Any number near 9 is a 1, any number near 0 is a 0, so those error terms are removed. That's why we only get 1 bit per coefficient. That's what makes it work. So we can do decryption of an encrypted message this way, which is just part of the code you saw above. You can decrypt a message and get it here, backwards, 1011. So that's how it works, and this is the wave of the future. Probably more important to learn than elliptic curves. I would think it's hard. We should all be moving towards this and away from RSA and elliptic curves and all the old stuff, which is all going away because of fear of quantum computers. So that's what I wanted to show you. And I think there's a comment in the Twitch. No, just an old comment. All right, I'm going to stop this video.